Welcome back. What questions do you have so far from the topics that we discussed? Okay. What we did in the last class was to look at the definition of Laplace transform. Okay, let's take it from the top. Okay. What we did was to start the idea of Laplace transform. Okay. You guys can see my screen all right, right? You guys can see my screen? Okay, Karen. Anybody else? Okay, good. All right, perfect. So this is what we discussed in the last class, Laplace transforms. Okay, I gave you the definition for a Laplace transform. Okay, let's see. The definition for Laplace transform is an integral over 0 to infinity. The function f of t, for which we are finding the Laplace transform, into e to the minus st dt. And s is in the frequency domain, right? And then I gave you the advantages of using Laplace transform, which is mainly arithmetic simplification, simplifying intuitive understanding and all of that. Then we looked at a step function and how to write any function, piecewise linear, sine, or other functions that have a particular on and off time using step function. Okay. If you do 2t u of t, this u of t turns it on, this minus u of t turns it off. Okay, so that's something we will use today in the example problems. Okay, then I had you write the equation for this using step function. Okay, from 0 to 1, the upgoing curve is on. From 1 to 3, the downward slanting line is on. From 3 to 4, again, the upward slanting line, this guy is on. Okay, that's exactly what we have figured out. And I gave you a method to find that M and C, the expression for the line, right? If you were to see this sine wave, how would you turn it on? And how would you turn it off? Okay. And then I went back to the idea that the definition of Laplace transform is that guy. There is a step function which can turn on and off. And then we discussed the idea of impulse function. Okay, discuss the idea of impulse function, which when you do an impulse function and when you multiply it, when you multiply it with a function, it has a shifting property. Okay, shifting property meaning the value of the function, okay, at that instant of time. I should probably write this as g of a. Okay, that's the idea of impulse function. That's how far we discussed. And then I gave you the Laplace definitions for Laplace transform for an impulse function is 1. The derivative of an impulse function has s. The nth derivative of an impulse function has s to the n. Okay. Then I gave you some functional definitions. Okay. If you have a function that is delta, what is its Laplace transform? If you have a step function, what is its Laplace transform? Okay. If you have t variable, what is its Laplace transform, so on and so forth. So we don't typically derive these from ground up. We simply use them. Okay, let me reproduce that table. This table right here is the is called the functional Laplace transforms because there are different functions. A sinusoid, um, t times e to the minus a, and e to the minus a t times sine omega t. All of these functions and their Laplace transforms. Okay, if you take a Laplace transform of this guy, you'll end up with that. If you were to take an inverse Laplace transform of this, you'll get this guy. Okay, so that's the idea. We don't derive them as often as we use them readily, look up. Okay, similarly, there's also an operational set. If you have a function and multiply that function, take a Laplace transform of it, how is the Laplace transform going to look? The Laplace transform is also going to be multiplied by k. Okay. Similarly, how can you manipulate if you were to take the derivative of a function and take a Laplace transform of it? Laplace transform of a derivative of a function. What do you get? Okay. S times the Laplace transform of a function minus these initial conditions. Okay. Initial conditions. I'll talk about that in an example. What about I have a function and an integral of a function, and I want to do a Laplace transform of an integral of a known function. Okay, then what you got to do is in frequency domain, it's simply the Laplace transform of the function divided by s. Okay, so this is where it really becomes handy. The advantage of Laplace transform is really apparent here. Okay, if you have a derivative in the time domain, in the frequency domain, it is s times f of s. If you have an integral, you only have f of s by s. So in the frequency domain, you don't have to deal with integrals. Okay, in the frequency domain, you simply have to deal with algebraic polynomial equations. Okay, as we will see shortly. But then you will see me using this table. This is 12.2 operational transforms. Okay, when you take a function f of t and perform some derivative operation on it, how does its Laplace transform change? Okay, that's how far we discussed in the last class. Okay, let's see. Questions, please. What questions do you have so far? Are we ready to move forward? Look at some examples. Okay, let's move forward then. Let's look at some examples. Okay. I'm going to look at I'm going to do some examples right out of your homework. Okay, that way, if you see 5 problems in the homework of the same type, I have solved one of those for you. Okay. One of the problems that you'll see on your homework is of this type, applying the definition of Laplace transform. Not just the definition, but the tables 12.2 and 12.1. Okay, here is an example. Find the Laplace transform of, so this is what I'm going to use, Laplace transform of t squared e to the minus at. You're asked to find the Laplace transform. Okay, so there are 2 ways to do this. Okay, there are 2 ways to do this. Let's see t squared e to the minus at is what we are interested in. This is what I'm going to do. Okay, I'm going to call this guy as f of t, and then there is f of t e to the minus at, because this is a format that is a that has a known Laplace transform. Let me go back, go to 12.2. Okay, 12.2. If you have a function f of t that is multiplied by e to the minus at, then all you got to do is start with f of s, and now your s variable is simply going to be incremented by a value of a corresponding to. So in other words, this gives f of s, this e to the minus at corresponds to a plus a. So if my t squared is f of f, is if t squared is f of t, let me find f of s for t squared, whatever that value is, okay, and then take it from there. So t squared is the function I want to, so if I were to find the Laplace transform of f of t, I'm doing 0 to infinity, f of t e to the minus st dt, implies since my function f of t is t squared, integral of 0 to infinity t squared e to the minus st dt. Okay, that's f of s, right? Now we can we know that 0 to infinity t squared e to the negative st dt. Okay, now this is a function, this is a compound function in the form of u dv by dt dt, or u dv format. Okay, so in other words, u is t squared, and then dv is e to the negative st dt. So we can use integration by parts. Okay, we have an integral that has two functions, u and dv dt. Okay, so in other words, u is the t squared. Okay, what's du? Du is 2t dt. Okay, and then we have dv equals to e to the minus st dt. So if I were to find v from this by integral method, I would have minus 1 over s e to the minus st. Okay, now we are ready to apply the integration by part, which says, here is where I'm using a formula u dv by dx. If I have a known form that looks like this, well, its integral is uv minus integral v du by dt, or dx times dx. Okay, so that's a integration by parts idea. Integral by parts. Okay, so we know what u is. We know what dv is. Okay, similarly, we have a value for v. We have an expression for v, and we also have an expression for du. Okay, so we should be able to apply the integration by parts mechanism, and once you do that, you can apply the 0 to infinity integral terms, and then you will find, okay, in the interest of completeness, maybe I will do this, u times v. right? That's this guy. U times V is t squared times negative 1 over s e to the minus st. Okay, all of that is from 0 to infinity. Those are the limits of the integral. Minus, now I'm writing the second term of integration by parts, which is this guy, integral, that guy. The limits of integral still remain the same, 0 to infinity. Okay, the limits of the integral still remain the same. Now v times du by dx. Okay, v times du by dx, which is minus 1 by s e to the minus st. That guy is v, right? That guy is v times du. V times du is 2t dt, right? 2t dt. So by observation, we see that this term goes to 0 for infinity. Okay, so because the reason is, if you pay attention, there is a t squared term, okay, that's going towards infinity as t tends to infinity, whereas e to the negative st term, all of this goes to 0. This goes to infinity, this goes to 0, but the second term, okay, that guy, e to the negative st term, goes towards 0 much faster than t squared. So the argument is all of this is going to go to 0. Okay, so we are left with something like this, just this guy, 1 over s or 2 over s integral e to the minus st 2t dt. So 0 to infinity. There's not a whole lot of magic I'm doing here. All I have done is just apply the definition, okay? Just apply the definition of Laplace transform to t squared, which is simply integrating 0 to infinity t squared e to the minus st dt. That's all I have done, okay? So once you do this integral, this is s, okay? 2 by s, what you have is it's 2t dt. I have already accounted for this 2t. So t dt e to the minus st t times dt. Okay, this should be a familiar form. Okay, this should be a familiar form, which is the Laplace transform of t. Remember, if you notice, this is the definition. This guy is the definition of Laplace transform of dt e to the minus st dt 0 to infinity. Now what we do is we know that this is the 2 by s Laplace transform of t. Okay, that incorporates this guy as well, because that's the definition of a Laplace transform. Now here it is straightforward, because from here, knowing that this is the Laplace transform of t, I can go back to my table, okay, and see what the Laplace transform of t is. Okay, I don't have to redo that, okay, because that has been, I can simply look it up on my table 12.1. Okay, notice that the Laplace transform of t is 1 over s squared. Hence, the Laplace transform of t is going to be 1 over which is going to be 2 over s cubed. So the Laplace transform of t squared is going to be 2 over s cubed. Okay, is that it? Are we done? Or do we have more to find out? Remember, we were interested in the Laplace transform of t squared e to the minus at. Let's not forget that, right? Let's go back. You don't trust me. Let's go back here. We are interested in t squared e to the minus at Laplace transform. Okay. In order to do that, okay, if you see here, I have the Laplace transform of t squared. If I have the Laplace transform of t squared, scaling it by e to the minus at is simply going to scale the S domain variable, add a to the S domain variable. Okay, this guy brings in this additional a. Okay, if you don't trust me, go to 12.2. Look at 12.2. You'll see that a function f of t, simply if you scale it in the time domain by an exponential, that's simply going to add a variable a, not a variable, a constant a, to the um, Laplace transform of f of t. Okay, so all we have done is to simply use that pre-solved problem. Okay, result from there. So if you see this problem on the homework, you know how to solve it. Not only this problem, if you are asked to solve any problem, Laplace transform problem, you know what to do now. You want to apply the integral 0 to infinity, the function of t, e to the minus st dt. Okay, everybody with me? Okay, let's see. Let's revisit this problem. Copy this. And I want you to think about if there is an easier method to solve this problem. Okay, method 2. Use Laplace transform, or how can you find the Laplace transform of this function using an easier solution? Okay. In other words, you can go back to these tables. Okay, I'll copy this. T squared e to the minus at. Okay, you can go back to these tables. You're asked to find t squared e to the minus at, the Laplace transform of it. You can use these tables. You can use these two tables, the one above and below. Okay, I'll give you a hint. I'll give you a hint. Okay, you know the Laplace transform of t e to the minus at, and then you also know the Laplace transform of t times a function. So my question is, can you put together a method in which, let me see if I can drag this further down, in which you can solve this Laplace transform of t squared e to the minus at using these two identities in a bit easier manner. Okay, let's see. Using the table, Ethan, thank you. Using the table, and this is how we are going to do. Let me demonstrate that to you really quickly. So one method of finding this guy was earlier when we used the definition, okay, t squared e to the minus st, 0 to infinity. I found the Laplace transform of this and then applied e to the minus at f of t form. Here, what I'm going to do is this guy, okay? I'm going to write this guy as the Laplace transform of t into t to the minus at. Okay. Then I have t times f of t form because this is known. Okay. T times f of t, you'll see that it is negative d by ds of f of t. Okay. Negative d by ds of f of t. Okay. So the idea is, if this is my f of s, f of t, and I already know the f of s for this guy from table 1, okay, then a function of the form, the Laplace transform of this function is going to be d by ds of f of s. Okay, let's see if we can do that. Now, f of t is t e to the minus at. That is what I defined it to be. From the table, we know f of s is equals to, if I go back to the table, the Laplace transform of t e to the minus at is 1 over s plus a whole squared. Okay, so let me copy that. The Laplace transform of this guy is going to be 1 over s plus a the whole squared. Okay, now I have the function and I have f of s. Now I'm interested in the Laplace transform of t f of t, which is the derivative of f of s okay. So once you do the derivative, you'll see that this derivative comes out to be 2 by s plus a the whole cube, okay, 2 by s plus a the whole cube, owing to the fact that there is a negative term here. So the Laplace transform of t squared e to the minus at, we just found out that to be this guy using two methods. In one method, we applied the definition of Laplace transform and arrived at the exact same result. In the other method, we simply used pre-calculated values, okay, and pre-calculated Laplace transforms to define that for us, okay, minus d by ds of, okay. Questions, please. What questions do you have? So the second method is more straightforward because it does not involve integration or integration by parts or any of that. Okay, we are simply taking off-the-shelf results. Okay, we'll do one more example. Okay, let's do example number 2, where you're asked to find out the Laplace transform of cosine h beta t. Okay, how do you find the Laplace transform of cosine h beta t? Okay, we have to use a few um, definitions that we did not encounter so far, but these are pretty straightforward trigonometric identities. Okay, but here is how I'm going to choose to divide it. Okay, cos h of t, I'll find the Laplace transform of it. Okay, once I find the Laplace transform of it, then scaling the time variable by using a factor beta, well, I can fix that. I can do that from the table. Okay, if I go back to the table tells me somewhere in here, okay, the table tells me that if I scale the time variable by a factor of a, well, all that is going to happen is that the f of s, the s variable is going to be divided by a, and the overall function is going to be a. So we have a way of going from f of t to f of at. So we'll use that. So the first thing I'm going to do is to find the Laplace transform of cos ht, then worry about cos h alpha t later, beta t, okay? The outside definition that I'm going to bring here is cosine h of t is e to the t plus e to the minus t over 2. That's a definition, that's a trigonometric definition that we should be able to Google. If you find out the similar to Euler's identity, e to the j theta, right? Similar to that, there is this relationship cosine h hyperbolic cosine t is, there's a relationship between exponents and cosine. Okay. Now, with this definition, I want to find the Laplace transform of cosine h of t. So we are still applying the definition 0 to infinity. Okay. Cosine h of t e to the minus st dt. That's the definition of Laplace transform, right? Now we can go ahead and do this 0 to infinity, and then in place of cosine h of t, you substitute et plus e to the negative t by 2 times e to the negative st dt. Okay, that comes down as is. Then you can do the integration. Then you can apply the uh, limits of integration, and you'll find out when you do the integration that the Laplace transform of cosine hyperbolic of t is really s by s squared minus 1. I'm not going to do this integration. Okay, all you have to do is take this e to the minus st inside, and then doing the integral of an exponential function is reasonably straightforward. I leave it as an exercise to you. Okay, Now from here, we are really interested in this guy, cosine h beta t. How do you get from this guy, which does not include the beta term, to this guy? Well, table 12.1 says Laplace transform of f of at is 1 over a f of s over a. Okay, by that definition, I'm going to say this guy is s over beta by s over beta the whole squared minus 1, all of that multiplied by 1 over beta. Okay, so by this definition. Now, from here, it's straightforward to show that the Laplace transform of cosine h beta t is really s by s squared minus beta squared. Everybody with me? So what we have done is to use operational Laplace transforms. Okay, some maybe we used functional Laplace transforms. And then of course we used the definition of Laplace transform. Okay. Questions, please. What questions do you have? Everybody with me? Okay. By a show of hands, how many of you started looking at the homework so far? After your midterm one, how many of you started looking at the homeworks? Okay, so if you did not already start looking at the homeworks, you probably should start looking at the homeworks and look at the examples and then see if you're getting into issues. Okay, so the examples that we are doing in the class should help you get started. So far, we demonstrated the use of operational, the table 12.2, 12.1, how you can look up and how you can be smart in applying the definition of Laplace transform, which is the integration, and use it very carefully. We don't, if we know the answer to something, we don't solve it again. Okay. So if we know something from table 12.1 or 12.2, we try not to solve it again. Questions, please. So now the premise of looking at Laplace transforms was that it makes our life easy when we encounter really hard, complicated circuit equations. Okay, let us see if that is the case indeed or not. That's what I discussed yesterday, right? Laplace transforms, if you do it in the frequency domain, circuit analysis becomes a bit more palatable, a bit more agreeable. Okay, if you're doing in the polar and rectangular form, Then sinusoidal arithmetic is straightforward. Okay. Similarly, if you're solving a lot of integral and differential equations, you better do them in the Laplace, in the frequency domain, S domain, um, because it makes our life easy. Okay, that was the claim I made. So I made yesterday. I did not quite demonstrate to you how. Let's look at that with an example. The third example of the day that we are going to look at is circuit analysis problem in uh, RLC components in frequency domain. Okay, let's say I have a circuit that has an inductor, okay, a resistor, and a capacitor. Okay, the inductance value is L, the resistance is R, capacitance is C. Okay, and then there is a switch here. The switch is on at t equals to 0, and it stays on. Okay, so if you look at the homework problem says um, this is given to be VDC, this is given to be V output. The homework problem asks, what is V output of S, or the Laplace transform of the output voltage? What's that? You're asked to find that out. Okay, and then of course you're given this to be I1, this guy to be I2, and this guy to be some I0. Okay, how do you find the output voltage? Okay, finding the output voltage is a matter of um, setting up KCL and KVL. Okay, the homework also says initial values are all zero. Okay, the homework specifies that the initial values are zeros, and I'll show you why that is important. Okay, now you're asked to find out the output voltage in its Laplace domain form. Okay, how would you go about doing that? Okay, so the first thing we write is this guy. Let us the solution. This is all part of the problem. Okay, let's do all of this in yellow, so I can write the solution in green. Okay, the first thing I'm going to do is to get a value for I1. I1, that's the capacitance through this capacitor. That's the current through this capacitance. We know is defined by the relationship I equals to C dV by dt, right? I1 is C dV by dt. Similarly, I2 is the current through the resistor, which is the voltage across the resistor by R, right? If you think about it, this resistor is in parallel to this capacitance C. So if the capacitance is at a voltage V0, the same voltage applies across R as well. Okay, so that's now, how about who can give me the value for the voltage across the inductor? What's the voltage across the inductor? Okay, everybody see the question? There is my inductor. I know one voltage on the left terminal, and um, I have a variable that defines the voltage at the right hand terminal. So what would be the expression for the voltage across the inductor here in terms of its terminal voltages? ZL times I is correct. Use the reactance of the inductor is correct. Correct. You're all right. So what I'm going to do here is simply going to, if you said ZL times I, you're correct. But we are still not using this ZL. ZL is J omega, right? So in the J omega domain, we would have done that. But here, just by observation, the voltage across the inductor is the difference between the left hand terminal voltage and the right hand terminal voltage, which is VDC minus VO, right? On this side, there is VDC that is being applied. And on this side, there is a voltage of VO. And then we know if we are not to write it in the frequency domain, J omega L domain, we know that it is going to be L di by dt, right? L di by dt. If I naught is the current flowing through the inductor, then the voltage set up by that uh, current would be L di by dt. Now from here, we should be able to write an expression for V out, which is this guy. Okay. Sometimes you see me using capital V, sometimes you see me using little v, VL, VDC, okay, and V naught, L di by dt. So V naught is VDC plus minus. So this guy from this equation, V naught would be L di naught by dt. Okay. From here, we should be able to get an expression for I naught. Okay. I naught is going to be V naught okay, or let me simply write it as negative L di naught by dt is V naught minus VDC. So di naught by dt equals to 1 by L times VDC minus V naught. Okay, so I naught would be the integral, okay, 0 to t of VDC minus V naught dt. Okay, we don't have to worry too much about this. We are going to get rid of this anyways. So all of these integrals, that's the point though. Okay, so I naught equals to VDC over L times t. Okay, if you do the integral of it, I'll spare you the details and do the integral of this guy. Okay, minus 1 over L integral 0 to infinity, 0 to t, V naught of t dt. Okay, V naught is a function of t. Okay, here, so the reason we want to do this is, if you think about it, we have an expression for I naught, which is the current through the inductor, that is splitting into I2 and I3. That's what I want to do. I want to apply KCL at that node. Okay, if I apply KCL at that node, I know that the current coming in is going to be I2 plus I1. That's what I'm after. Okay, I have expressions for I2 and I1, which I'm going to copy from here. Okay, I have the values for, or the expressions for I2 and I1. Okay, so if I copy it here and apply KCL at node 1, let's call it 1. Let's go back. Let's call it node 1. Okay, if I apply KCL at node 1, I know for a fact that I naught, that is the current coming from the left branch inductor, is going into the resistance and the capacitance. Okay, so what I have done simply is to set up the current equations, current voltage equations. Okay, this should really be VDC. Okay, now I can write these equations in terms of their the knowns. Okay, I naught is going to be LDC. Here it's going to be U of t. Okay, because it's turning on at t equals to 0. Okay, so the idea is I naught equals to I1 plus I2. So integral, so VDC U of t by L, that's I naught, minus 1 over L, integral 0 to t, V naught dt. All of that is I naught, right? So I naught, that's the current coming in from the inductor. Okay, that's going to be V naught over R. Okay, V naught over R, that's the current in the resistor, plus C dV naught by dt. Okay, everybody with me? So there's an equation here, VDC U of t by L minus 1 over L integral 0 to t. It's the same equation, I'm writing it again, equals to V naught over R plus C dV naught over dt. You can rearrange this. Okay, you can rearrange this in this format: V naught over R plus C dV naught over dt. Okay, plus 1 over L integral 0 to t V naught dt equals to VDC U of t by L. Okay, here I have the equation that describes, so this is simply the KCL at node 1. Okay, and I promised you that Laplace transform is going to make our life easy. Okay, and see how. If you did not have Laplace transform, you would have had to solve this equation that is that has a derivative and that has an integral. Okay, but look what I'm going to do. From here, I'm going to take the Laplace transform. Okay, if I take the Laplace transform on both sides, V naught over R, okay, is going to come out to be V naught of S over R, because R is a constant that does not change. So the Laplace transform of V naught meaning V naught of t, right, gives you VO, V naught of S plus C dV naught by dt. If I can take the Laplace transform of that guy, Laplace transform of C dv naught by dt. Okay, let me refer to the table here. We go back to the table right here. If I have a function's derivative, and I'm trying to take the Laplace transform of it, okay, what I get is s times the Laplace transform of f of s. Okay, so let me see. So if I have a function VO and I'm trying to take the derivative of that Laplace transform, then this Laplace transform, we can take C outside, we can leave C as is, okay? C, the Laplace transform is going to be S, f of s minus f of 0 minus, which is the initial conditions. That's the initial condition given to be 0, okay? So what we are left with is C coming in from here times the derivative of a function when you Laplace transform it, it gives you C of f of s, which is C times V of s. Okay, so all I have from here is the capacitance that's giving me C times S V of s. Okay, that's all coming from this term here. Okay, if you want, I can color code that. This guy, the Laplace transform corresponding to that is this guy. Now pay attention. So here is the advantage. Instead of having to deal with the derivative, first order or even second order, I have converted it into an algebraic form, S VO of S. Okay, I converted it into an algebraic form. Plus, now let's do the integral of V of t dt, integral V naught of t dt. Let's see if we have a Laplace transform table from the table there. Okay, if I go back to the table, the table tells me you have a function which I'm trying to integrate and take a Laplace transform of that function. Well, all it has to be is fs over s. Okay, straightforward. So that much is straightforward. So if I'm going to look at this guy, the integral, and take a Laplace transform of this integral, okay, then this 1 over L is coming from there. Now an integral has f of s, okay, the Laplace transform of the function itself, okay. So Laplace transform of V naught is V of s, okay, divided by s, okay, that divided by s. That gives the Laplace transform of the blue highlighted function. Okay, everybody with me? So all we have done, the purple part, the Laplace transform corresponding to that is down below. The green highlighted part, the C dv by dt, has a Laplace transform equivalent, and the integral part has a Laplace transform equivalent. We still have to take care of this guy. Okay, we still have to write the Laplace transform of that guy. How do you write the Laplace transform of that guy? Well, we can go back to our table again. We'll go back to our table again, which is VDC U of t over L. Okay, if you have U of t, if you have U of t, its Laplace transform is 1 over S. Okay, that's what we are doing here. We have a U of t in the top. So that's going to give us on the right hand side VDC over L. U of t is Laplace transform is 1 over S. Okay, 1 over SL. Did I miss something here? Okay, so let me write this equation again. V naught of S by R plus C S V naught of S plus 1 over L V naught of S times over S equals to VDC over SL. Okay, I multiply both sides by S. I got S times V of S, okay, over R plus C S squared V of S plus 1 over L V of S equals to VDC over the S domain. What we got is VDC over S squared L. Okay. Or let's divide instead of multiplying. Let's divide by S. Okay. We'll divide the whole damn thing by S. Okay. Once we divide all of this by S, what we have is S squared. Okay. All I have done is simply divide this by S. Okay. When you factor out, or maybe I was just missing. Let me go back really quickly. So what we have done is we use the fact that this guy ut is 1 over S. Okay, and then we have derived so far. So the important thing that we want to remember at this point is that the idea that we want to remember at this point is that what were once, okay? If you go back here, in the time domain, we had derivatives and integrals, integral differential equations, okay? Now what we have is not integral differential equations. We have equations that have variables of S, polynomial variables of S. Okay, have polynomial variables of S. So let's continue from there. Let's continue our discussion from there. Okay. Now, VDC over S is the right thing. So we'll not worry about this SL. Okay. Now it's a matter of So forget that you have been through the pain of um, derivative integrals and multiplying and all of this. All you want to do is to treat this like the polynomial in S that it is. Okay, so what you get is 1 over R. Okay, um, V naught over R. So you have something that looks like 1 over R plus CS plus 1 over LS. Okay, that equals to VDC over SL. Okay, you can manipulate this any which way you want. You can manipulate it in a bunch of different ways. Okay, and then you will end up with the result once you massage this equation that V of S is going to be VDC over RC. Okay, by VDC over RC by S squared plus 1 over RC times S plus 1 over 1 by LC. Okay, VDC. Okay, so the manipulation from there is more or less straightforward, which is simply you take VDC over S, multiply this S, L on both sides, and then um, do some uh, do some simple algebraic manipulations. All you want to remember is don't forget the fact that this is a polynomial in S. Okay, this is a polynomial in S. The denominator is a polynomial in S. The numerator is a constant VDC over RC. Okay, VDC over RC. Okay. Questions, please. So this is what we were after. We were asked to find out this guy, the Laplace transform VO of S. We were asked to find that out. Okay. Questions, please. What questions do you have? Okay. Let me go over this problem again really quickly in a um, summary manner without getting lost in the details. Okay. You're given an RLC circuit. There's a L. Okay. There's an impedance. There's an inductor, followed by a resistance and a capacitance. Okay, you're given that the output voltage VO is across the capacitance, and you're asked to find out VO of S, or the Laplace transform of the output voltage. So all you have done really is to notice that the current I0 that is coming in through the inductor is splitting into I1 and I2, which is the same as KCL at this node. If you write KCL at this node, it will tell you that the currents coming in is equals to current going out. Hence, you can set up that equation. I1 plus I2 is I0. Okay. Now, I1 is a capacitance through the current, current through the capacitance. I2 is a current through the resistance, and I0 is a current through the inductor. Okay, so you put together the current through the inductor is splitting into the resistance and the capacitance. Okay, once you write it out, you're going to get an equation that looks like this in the time domain. The inductance, current shown in, well, at this point we can't see them as inductance and capacitance. But the idea is there is a derivative and integral in time domain, which is very complex to solve if you want to find a solution to V0. So what you do is to translate this equation. You want to translate that equation in the Laplace transform, in the Laplace domain. Okay. So in the Laplace domain, what you got is VO of S over R plus C times SVO of S. Okay. A derivative of a function, derivative of V0 function. The Laplace transform is that guy. And then you wrote the Laplace transform of all the derivative and integral functions of all the terms in the equation. Then it's just a matter of algebraic simplification. The important thing to note is, whereas in the time domain, we had equations of derivatives and integrals. In the S domain, they're all in terms of um, polynomials of S. Okay, you don't have integrals and derivatives that complicate our equations here. Does it make sense? So what we have is the what we have is the polynomial equations. You can massage this. You can multiply both sides by L and both sides by R, so on and so forth. Okay. If you multiply both sides by R, you get this RL, you get this RLC, and then you get this L over here. Okay. So you should be able to from there calculate, give an expression for okay. You should be able to write an expression for VO of S. That's what you're asked to find out. The Laplace transform of the output voltage. You can massage it. V dc S squared plus 1 over RCS. Okay. We like this form because if you think about it, the Laplace transform of the output function is in the form of some constant by a polynomial in S. See, S squared plus 1 over RC times S plus 1 over LC. So that's a constant. This is a constant. So what you got is a neat little polynomial. No more derivatives. It's a polynomial in S. Okay. VDC over LC for the numerator. Let's see. VDC over LC is right. You know what? You're correct. VDC over LC by S squared plus 1 over let me give you the, I think I may have this part wrong. Okay. The solution really is, if you rearrange this, you should get something that looks like this. Okay. V output over S equals to VDC over LC. You're right. If you got that in the numerator, you're very correct. S into S squared plus S by RC plus 1 by LC. So this is what you should have seen for your V of S. So thank you for double checking. Zoe, thank you. Okay. So again, the important thing is the Laplace transform in S domain is going to be some constant by a variable S by another polynomial, okay, by a polynomial in S, okay. Okay, whereas V of t in the time domain, it had some derivatives, it had some integrals, and it had some crappy terms, which is not the case in frequency domain. Questions, please. What questions do you have? So as you can see, Zoe privately sent me that I may have sent me a message that I may have incorrectly calculated the result here. Okay, so what questions do you have at this time, please? Okay, the question I have for you is, well, the problem asked us to find this guy, we found it, but why do we need it? Right? We need it because eventually we are interested in finding the V output. What is the output voltage in a time domain? Remember what we were doing for the um, polar rectangular forms? We started out with V of t, okay? Vm cosine omega t plus theta. We wrote that as Vm angle theta, okay? Then we did all our math. If there was an I of t in some Im cosine omega t plus theta c, we did some gymnastics. Im angle theta c. Okay, we did all our v times I, v over I times I squared times v, whatever we wanted to do, we did it in the polar and rectangular domain. And then when I had v0, v output of theta output, I eventually had to come back to the time domain, right? So I had to go from the phasor form, from the polar form into its time domain form. That's exactly what I got to do here as well. Okay, so once we do all our calculations in the in this form, okay, from V of S, we have to take an inverse Laplace transform. V of S, if you take an inverse Laplace transform, that will give us V of t. This is what we are interested in eventually, right? So that brings us to the notion of inverse Laplace transform. Okay. Let me see if I can go to the notes here. So everybody with me? So that brings us to the notion of inverse Laplace transform. So if you go back to the notes posted for this class, there should be a section, okay? There should be a section 12.7 that talks about inverse Laplace transforms, okay? Section 12.7 is inverse Laplace transforms. I'm going to leave that as an exercise for you, okay? So we will not be meeting tomorrow, Wednesday, or we will not be meeting on Thursday. what I want you to do is to go through these notes, okay? Go through these notes, and of course, go through the videos by Tetro, okay? Go through the videos by Russ Tetro, 12 point. We looked at 12.6, applying the Laplace transform, okay? I want you to look at, I want you to see videos corresponding to 12.7, okay? So that's tomorrow and the day after. Spend time on 12.7 and work on homework problems corresponding to 12.1 to 12.7. Okay, we will come back and meet on Monday of next week and look at 12.8. Okay, then we can also look at example problems as well. Let's see. Questions, please. What questions do you have?